All right, and let's go to the agenda now that we've had a chance to talk about this free body diagram to warm up. And the reason, like I said, that we're going to do a lot of free body diagrams is when we solve problems, we're going to use them today to solve a couple problems at the very end. But if you don't draw a free body diagram for complex scenarios, it's really easy to get lost, especially when we start talking after Thanksgiving. We'll maybe bring it up a little bit before Thanksgiving on Monday, but especially after Thanksgiving, we'll be digging into a lot of angled forces and objects on slopes. And so if you don't draw a free body diagram, you can miss things and you won't necessarily catch which things cancel and which things don't. And we always are wanting to try to figure out what the net force is. So in this case, the net force is just that friction force because the normal force and gravitational force cancel. So just wanted to warm it up. We'll warm up the class with that free body diagram. We'll be doing a lot of those. So there's our bell ringer. In terms of test corrections, we're going to take some class time here in just a few minutes to do that. Those are due next Monday. So you need to get those submitted on Axis. Remember, you'll do them on a separate sheet of paper. And then submit those on Axis. And then if you'd like to do a retake, today is your first day, your first opportunity. So you can come at 4 o'clock today if you want to and you feel ready. You can also come at 4 o'clock tomorrow, or you can wait and take it at 4 o'clock on Monday. So those are your three options for retakes. Make sure you're thinking through what schedule works best for you. Pick your time, put it on your calendar so you don't forget. And it'll be 4 o'clock each time. You do have to have the test corrections done first before you're eligible to take the retake. And do remember that if you do the retake, that will become your final score. Please remember that on Axis right now, I have put your curved grade in. So right now you have already the curved grade benefit, even though most of you haven't done the corrections or at least haven't submitted them yet. So until you get the test corrections submitted, right now you have that curved grade in there, but if you don't get this submitted, you won't get to keep that curved grade. So next Tuesday after Monday night, and I've had a chance to see that you've submitted your corrections. If you haven't submitted them, then on next Tuesday, I'll be reverting your grade to the lower uncurved score. And you can see what that uncurved score is by looking at the comments on Axis. So this time I just did it in the reverse order. So I put the curved grade in first, and that'll probably mean I only have a few, if any, that I need to change in the end. As long as you get the test corrections, you keep it the way it is. All right, so what we're also going to do today is a very short bit of force notes on forces, a further introduction to Newton's laws and applying them by thinking through net force, thinking through acceleration, thinking through free body diagrams and how it kind of pulls it all together. It'll just be maybe 10 minutes, a pretty short section after we finish with test corrections. And then after we're done with those notes, you'll have a chance to either finish your test corrections and submit them or work on positive physics. Remember, the Unit 5 Introduction to Forces assessment is due right after Thanksgiving break. So for you guys, it'll be that Monday night. For B-Day, it'll be that Tuesday night. But I'm giving you a little bit of time today to potentially work on that. And I'm not giving you any other worksheet assignments prior to Thanksgiving. Just getting the test corrections done, doing a retake if you want or need to, and then getting that positive physics assessment done. So that's the only outside of class work that I have for you tonight. I had asked you to do some readings after Monday's session, but for tonight, nothing new, just test corrections and positive physics. And same thing next Monday, nothing new. We'll do some work in class, but nothing new in terms of assignments. Will just be the same thing, wrapping up those test corrections and doing the positive physics assessment. All right. Any questions about the timelines, deadlines, due dates, anything like that before we jump into test corrections? Okay. Let's look at the test corrections then. And I would encourage you just follow along, do your test corrections while we're going. If you can't quite keep up, that's fine. You can always finish them later, but jot down some notes. Remember your test corrections, as I said a few minutes ago, they do need to be on a separate sheet of paper. Make sure you number the questions. If you missed one of the multiple choice questions, you need to say what the answer is and then give some sort of indication that you know why that's the answer. So doesn't even necessarily need to be a full sentence, but some sort of clarification as to why you know what the answer is. So just saying, for instance, the answer to number 1 is B doesn't help me know that you now understand it. And that's what I'm trying to discern is, do you now understand it? Okay. And then for the free response questions, If you only miss something like sig figs or a unit, you can just rewrite the answer that's corrected. You don't have to show your work again if your work was already correct. But if you missed any part of the work, then you'll just need to rewrite your answer. If you had a very small error in more of like an essay-ish kind of thing that wasn't more math driven, you can just kind of, instead of rewriting everything, you can just write an addendum. So you can say, originally I said this, that was wrong, it should be this, something like that. You don't have to necessarily rewrite the whole thing. Again, you just need to clarify to me that you understand what you missed and why, or what you needed to add, like if you forgot something that should have been there, something along those lines. If it's more math based, you don't really need to explain it. Just show me the math that either you didn't do or you did wrong. All right. Any questions on formatting your corrections or processing your corrections? Okay, for number one, the x and y components of vector A in the image above may be stated as either. And so they give you a couple options based on either the theta angle, which is the one we would more traditionally look at, or the alpha angle, which is less traditional, but can use it. It's an angle referenced to this resultant hypotenuse. So we can make the x and y components below it or above it, either way. And normally we would make it below it in this case, and our x component would be the cosine of theta, or we would use the cosine of theta to find it, and we would use the sine of theta to find the vertical component based on this. And if we look through our examples, all the first half is all about the alpha. It's all about this top triangle if you made your x and y above the hypotenuse. But the second half of all of them is about the theta, which is what we would normally do. And the only one that lists your x as based on cosine of theta is b. So really, you don't even need to look at anything else. If you recognize that's the only one that has a cosine theta for the x component, the rest all use sines. So those are incorrect. So it's just b is the only one that can be true. Now you can go back and prove that this is correct. If we base it on the alpha angle, on that angle, x ends up being opposite, so we have to use sine. And the y ends up being adjacent, so we have to use cosine. So that's not the traditional way we would do it, but based on trig, we can. We just have to be careful that we recognize it's not the normal cosine for horizontal if we go to that angle. Questions on number one? Really almost more of a trig question than a physics question, but you need to know that trig pretty well to be able to do the physics for other problems. All right. Number two, a particle has a velocity component of 4.8 meters per second due south and a velocity component of 7.1 meters per second due east. The magnitude and the direction of the resultant velocity are. So I just on here, and as you can tell, I'm adding things on here so you can visualize it as we talk it through. So those x and y components I've drawn on here. Those are the kinds of things I would encourage you to do on your scrap paper while you're taking a test. Draw it out, sketch it out, so you're not trying to do it all in your head. So I would sketch something like this on my scratch paper just to make sure I understand the situation. I drew a downward red arrow for the 4.8 meters per second south and a sideways blue arrow for the 7.1 meters per second east. And then the resultant would be the hypotenuse that connects those two and develops a right triangle. And if I use Pythagorean theorem to find what that hypotenuse is, only b gives me the correct value. So I don't even really need to find the angle. But I do want to emphasize, so this is a little bit of a spoiler in some degrees for the retest, there are multiple versions of question one and multiple versions of question two, where sometimes you do need to think through more than just like on number one. As soon as you recognize a cosine theta is the only one that's correct in this part, you're done. But you might have to think about a little more than that if you saw a different version of this question. Same for number two. There might be multiples where the hypotenuse was correct and you do have to think about the angle. So I do want to talk about it briefly. If I look at this angle, this one that I've drawn, this theta down here along between the green and the blue, would be equal in value to between the green and the x-axis. They're internal opposite, right? So those two angles would be would be equal. And the angle within the triangle is a little bit awkward in terms of defining the direction because of the way it's shown. So understanding that that is also this angle, that's a little clearer. This green hypotenuse relative to east is south of east, right? So that is correct. It's 34 degrees south of east. We didn't really need to prove that to answer this question, but you might on a different version. And so recognizing that you can define it based on your east reference. You could also figure out how far east from south it is. That would just be this other internal angle. But depending on how they give you the directions, you may have to do a little geometry and figure out which angles they're referring to. North of east doesn't make sense because this green line is not going north at all. It's only going south and east. So you can eliminate A and C pretty quickly. Questions on number 2? All right, question number 3 is classic College Board. All kinds of distracting information that's irrelevant. So the only thing you really need to focus on is the X and Y components that are given. If you note, because if we think about projectiles, the thing that determines the range, right? The equation is X equals V times T, right? The displacement equals velocity times time. And we're talking about the horizontal velocity and the time of flight. So if we look at these, all of them have the same horizontal velocity. So that is not impacting any of them different. So that's a moot point. It's important to notice, but once we see they're all equal, we don't need to think about that anymore. So the only thing we need to think about is time. And what controls the time is the vertical component. So the vertical component is shown here. So the mass is irrelevant. The hypotenuse actual velocity is irrelevant as long as they're giving us the X and Y components. We just need to figure out which of these Y components would maximize the time since the X components are all the same. And the Y component that's the largest gives it the most amount of time in the air. So this 86.6 meters per second gives it the greatest amount of time in the air. So the angle is even irrelevant. I mean, it's irrelevant in the sense that we don't even need to worry about what the angle is, because as long as we focus in on those components, we have enough to answer the question. They're definitely trying to get you to be distracted, and that's what College Board does. They often give you a lot of information that is true but irrelevant or unnecessary. And this one especially showing you the 45 degrees, a lot of students latch onto that 45 degrees because that is an important concept, that if everything else is the same, 45 gives you the best range, but not everything else is the same in this case. And the example for Cannon D, it's got a much larger overall velocity, which gives it a much larger vertical component. And so the fact that it's at a higher angle actually helps it have more air time. And because it's at a larger overall velocity, it still has the same horizontal. So the focus is, and that's a key for AP tests, is beginning to develop the skill to distill down what's important. And it's a skill that you'll continue to grow at and get better at as you do more and more. One comment I'll make, the multiple choice questions are always like that, where you have to distill away the things that are unimportant and focus in on what helps you answer the question most directly. The best way you can practice is something I've been encouraging you for a while. Get onto that AP classroom, practice those multiple choice questions. We don't really do a lot of in-class practice multiple choice questions. So that's why I keep reminding you, go to that AP classroom. There's a bunch of them on there. And just so you know, as I looked back to see after the test how many people actually went onto the AP classroom and tried some of those multiple choice questions, I think there were only 4 or 5 students out of 70 that did any of them. The one student who got a perfect score on this exam did all of them. So I don't necessarily know that you would need to do all of them to get a perfect score, but that showed a real dedication to practicing. And in this test, actually, the multiple choice was harder for a lot of students than the free response. The free response this time was much more math driven. So for those of you that are good at math, you probably found the free response easy. The multiple choice is much more, can you decipher the information and distill away what's irrelevant and focus in on what's important? So they're really testing at a higher level. How can you piece together what's truly important for each question? Anything you want to ask about number 3? All right, number 4. 3 stones of different mass, m, 2m, 3m, are shown and thrown vertically upwards with different velocities, v, 2v, and 3v respectively. The diagram indicates the mass and velocity of each stone. Rank from high to low the maximum height of each stone. Ignore air resistance. So if you recall from the FET simulation that we did, you went through a whole sequence of gathering data and came to the conclusion that mass was irrelevant. So that's one way. If you remembered that from the PhET, you could know that mass is irrelevant. If you didn't remember it from the PhET, if you just look at the three main kinematics equations that we've learned, only two of them have anything to do with finding height, and neither one of them has any element of mass in it. So even if you didn't remember from the PhET that concept, looking at the equations and recognizing mass isn't even part of these equations, it's all based on the acceleration and the time and the velocities. And so that's the only thing that's relevant. And so because the velocities are different, that's what's going to give it the greater displacement. If we look at this second kinematics equation, it's the one that's really applicable. The initial velocities are all what's different. The acceleration is going to be the same because it's just gravity. And so the time is going to be different for each because the velocities are different. But we can see this velocity is going to, increasing this velocity is going to increase this vertical component. So that's a couple ways you could kind of think through number 4, depending on how well you remembered the PhET versus how well you understood the kinematics equations. Questions on number 4? You could also think through number 4 with forces, but we're just now learning those. So that would be an additional way. So you could see a question like this again with a slight different twist on your forces test, because now that we're learning about forces, that's a different way to think through it. It's not particularly helpful on this question necessarily, but if they just tweak the question a little bit, the same kind of thing could be asked and it make it a force question. So a little bit of a spoiler for upcoming tests, if you remember that. Number 5, the free fall trajectory of an object thrown horizontally from the top of a building is shown as the dashed line in the figure below. Which set of arrows best corresponds to the directions of the velocity and the acceleration for the object at the point labeled P on the trajectory? Ignore air resistance. So, well, if we're ignoring air resistance, the only acceleration is due to gravity. So it has to either be A or B, because gravity is always towards the center of the earth or down. So it can't be C or D, just based on the acceleration. And if we look at the components of the velocity, at the very top, it only has a horizontal component. So its actual velocity is its horizontal component. But at every other position, it has two components, and its actual velocity would be the resultant of those two. So at point P, the actual velocity would be the resultant of the vertical and horizontal components. So it would be pointing tangent to that parabola. And that would give us this selection A. Questions on number 5? All right, number 6. A rubber ball is dropped from a height of 2 meters, hits the floor, then rebounds to its original height. Which of the following graphs would best represent the height, distance above the floor, versus time for the bouncing ball? Ignore air resistance. So this is seeing, do you really understand position time graphs when there's an acceleration? And so in this scenario, we know that there is an acceleration because gravity is going to be drawing it down as it falls. And so if we think back, position time graphs, if there's an acceleration, have to be curved. And so A, B, and C all have curves. D does not. So that right away eliminates D. If we remember, position time graph slope tells us velocity, we can also eliminate D because the slope is constant on the way down and constant on the way up. And we know there is an acceleration due to gravity. So it does not remain constant, to be speeding up on the way down and slowing down on the way up. So D can't be right either way you look at it, whether you're focused on slope or whether you're focused on just the shape. If we think about a B, it shows the distance going below the ground. So that doesn't make sense. We can pretty quickly eliminate that one. And then so for A and C, we're just trying to figure out which one shows the correct changing velocity, which is the correct changing slope pattern. Well, if it's dropped from being held, it's going to have a very small initial velocity. Well, it's going to be 0 at the initially, but it's going to then have small that's growing faster and faster. So that matches C. It has 0 velocity initially, and then it's small, the slope is shallow, and then the slope keeps getting bigger and bigger and bigger. So this shows it's speeding up as it comes down as time passes. And then it's going to bounce and start going back up. As it starts going back up, it's going to have a large velocity initially, but gravity is going to slow it down until it reaches its peak, and it's going to actually have that 0 velocity at the top vertically. So this is the one that fits. And the acceleration due to gravity is what's causing this curved shape in the graph. So that's why C is the answer for number 6. And understanding that also helps you understand how to answer 7. Which of the following graphs best represents the acceleration versus time? Well, it's the acceleration due to gravity is what's causing this speeding up and slowing down. And so before and after the bounce, it has to be negative 9.8. A, there is no negative. C, there is no negative. And D, it's only negative before the bounce. So B is the only one that shows it being negative before and after the bounce. What happens in the middle, whether you understand it or not, doesn't really matter. We'll learn more about that now that we're learning about forces, why it looks this way. But the key is recognizing that it has to have a constant acceleration equal to the acceleration due to gravity before and after the bounce. What happens during the bounce doesn't really matter because the other graphs don't work when we focus in on the acceleration before and after. Questions on number 7? All right, keep moving. Number 8, sphere A is projected off the ledge 1 meter high with a horizontal velocity of 2 meters per second. Sphere B is simultaneously dropped from the same height as sphere A. Both spheres have the same size, shape, mass, and air resistance is negligible. So 8, which sphere will be in the air for the greatest amount of time? Well, when we find the time, it's all based on how high it is. And so they both are 1 meter high. They're both falling exactly 1 meter. Their vertical displacements are the same. Their initial velocities are the same. They both would start with an initial vertical velocity of 0. So since their initial vertical velocities are the same and their heights are the same, their delta y's are the same, and the acceleration in both cases is only due to gravity, they would both fall for the same amount of time. It's basically just thinking through the second kinematics equation, showing you at the same height and same initial velocity and the same acceleration, their times will be the same. And then for 9, which sphere will have the greatest vertical speed at the instant of impact? You could think through like VVAT. The initial velocity is going to be 0 for both vertically. And the time we just figured out for 8 would be the same. And the acceleration's due to gravity. Or you could use the third kinematics equation. The distance they're falling is the same. The acceleration's the same. They both have the same initial velocity. So in both cases, you could use either of those equations to verify that the final velocity, vertically speaking, would be equal. And they often interchange velocity and speed because when they say speed, they're just wanting you to focus in on the magnitude and not worry about the direction, which here they could have just as well said vertical velocity and it wouldn't have changed the question. But just so you're aware, they often do just interchange speed and velocity when they really want you to focus on the magnitude and worry less about the direction. Questions on 8 or 9? All right, number 10. Number 10 is really challenging whether you remember about the lab we did where you worked in groups and you looked at the data with the moving man and you graphed the position time and then you took from that sequence to find the velocity, and then you graphed velocity versus time, and then you took from that the acceleration and you found the relationship of the 3 kinematics equations. It's basically kind of challenging you. Did you really understand what you were doing with that? And so it says the table shows vertical position as a function of time for an object that's dropped from a height of 5 meters. It's vertical instead of horizontal, but so in this case, we actually know what the acceleration should be, but maybe they're wanting you to see, does air resistance make a difference? Does it actually change it from 9.8? The student must determine the acceleration of the object. So we would assume it should be pretty close to 9.8, but maybe there's enough air resistance that actually changes it a bit. Which of the following procedures could the student use to make the determination? Justify your selections. Select 2 answers. So in each answer, each option, there's an answer with a justification. So they start off with something, then they say since, and then that's their justification. And you see they all follow that same pattern. So for A, use basically the second kinematics equation we learned. Since, your justification, all quantities are known except for the acceleration due to gravity. And we can assume that the acceleration should be close to the acceleration due to gravity, but apparently here they want us to prove it. Or maybe identify that air resistance did matter. So we do know everything. We can look at the graph. We know final position. We know initial position. We know the time. And so we know the initial velocity because it says it was dropped. So its initial vertical velocity would be 0. So we do know everything except for A. That does work. The method works and the rationale for why it works fits. Letter B, create a graph of y as a function of t squared. Okay, so that's what they're saying you could do. And we actually did that. You linearized your graph and made it position versus t squared. So that seems good. And then the justification is, since the slope will be equal to the acceleration due to gravity. But what we discovered when we did that lab is it isn't actually the acceleration, it's 1/2 the acceleration. The slope isn't the acceleration, it's half of it. So the beginning is good, but the rationale is not quite right. Had they said would be equal to half the acceleration, then they would have been right. But that little detail there makes B incorrect. C, create a position versus time graph of the ball's motion. That seems logical. Use the data to create a velocity versus time graph of the ball's motion. That's exactly what we did in our lab, took secants and made velocity time graphs. So that makes sense. So here's our justification. The slope of the velocity versus time graph represents acceleration. That is true. The slope of a velocity time graph does represent acceleration. And so everything about C is accurate. For D, use Vy equals delta y over delta t to determine the average vertical speed of the ball. Okay, that is a true statement. And then divide the average speed by time in which the ball was in the air. Okay, we could do that. So far, it doesn't necessarily seem logical, but they haven't said anything wrong yet, since the average speed in the time interval is used to determine the object's acceleration. Okay, there's where they went off the rails. The method isn't very logical to begin with, but the rationale is for sure wrong, because acceleration is not average speed divided by time. Acceleration is change in speed divided by time, or change in velocity divided by time. So the average wouldn't help us do that directly. We would have to do some manipulation from that. So that one's not right either. It's not a very logical process, and the rationale is just mathematically incorrect. There, you will continue to see more and more of these select 2 answers. Typically on the AP exam, the last 3 to 5 questions all have select 2 answers. So the first 45 to 47 are all normal, and the last 3 to 5 are always select 2 answers. And so want to give you some practice at doing that. You do have to get both right to earn credit. Questions on number 10. All right. For most of you, I think since the free response questions were for the most part very mathematically driven, a lot of people did really well on the free response, and some of you struggled a little bit more on the multiple choice this time. So I wanted to spend some time going through those. For number 11, a child goes due north for 30 meters, then turns a corner and moves due east for 20 meters. Describe how you would draw the 2 displacement vectors and the resultant. So the key is here making sure you say that the 2 vectors, the 2 displacements, would be the legs of a triangle, and that the resultant would be the hypotenuse of that triangle. You could describe it in a variety of ways. A lot of you went into great detail. And so this just says draw an upward vector to represent the 30 meters displacement, then draw a vector at a 90 degrees to that to the right, which is representing the east, and make it shorter since it's only 20 meters. Draw a hypotenuse that forms a triangle between those 2 vectors. That hypotenuse is the resultant. So you had to have those components there of the displacements are the legs, and the resultant is the hypotenuse. It had to be clear either by saying that it was the hypotenuse or saying that you connect the tail of the first vector to the tip of the other. So there had to be clarity that it was the hypotenuse of a triangle one way or another, either using the word hypotenuse or describing how you drew it precisely. For part B then, what is the magnitude and direction of that resultant? So I just drew the 30 vertical for north and the 20 horizontal for east. The hypotenuse is just using Pythagorean theorem, and the 20 and the 30 were both given with 3 sig figs. So my hypotenuse should also reflect those 3 sig figs, 36.1 meters. And then to find the angle, you could find it as I did here with this theta. That would tell you how far east it was from true north. And so that would be the tangent of this would be opposite over adjacent, so 20 over 30. So that's how I set this up. So that angle is 33.7 degrees east from due north. You could also find this angle down here, which I've labeled as alpha, and you could find it using tangent of 30 over 20, because that would match this other internal angle, or you could find the 33.7 and subtract it from 90. You don't really have to find it that way, but some students did, I think mainly because most of the time in math you represent it from the east, or you just said it was rotated up from horizontal, and that's how you would normally describe it in math class, which is fine. So you can do that. But giving the 33.7, as long as you said it was that's how far east from north it would be, is also acceptable. Both ways are fine. Questions on number 11? Okay. Number 12. A freight train is traveling over a bridge 90 meters above a river. The train is moving at 39 meters per second when a package falls out of it. What is the horizontal distance between the point where the package falls out of the train and where it lands in the river, ignoring air resistance? Express your answer with the correct number of sig digs and correct units. So this is like the airplane problem we did in class, where the airplane dropped a package and it fell as a projectile till it hit the ground. It's the same steps we did on that example. It's just now coming out of a train and falling to the ground because the train happened to be on a bridge. So we need to find how long it's in the air, and that's going to be based on the vertical data because that's what we know. We know how far it fell, 90 meters. And it would start with an initial vertical velocity of 0 because it just fell out of the train. So it wasn't thrown down or launched down, just fell off. So the second kinematics equation we learned is probably the best route in terms of finding the time, because we know that the displacement vertically is negative 90 meters. We know the initial vertical velocity is 0 because it just fell, so it didn't have an initial vertical velocity. And we know the acceleration is due to gravity, and we can just solve for t and find with 2 sig figs that would be 4.3 seconds. Now, whether you showed sig figs on the time or not doesn't matter, because the time isn't the final answer. So you could round the time or not. You do need to round your final answer though. So when we find the actual range, horizontally speaking, it's the horizontal velocity, which was given, 39 meters per second, multiplied by the time. There is no horizontal acceleration, so the whole 1/2 at squared doesn't matter. You can write it if you want, or you can ignore it. But you do need to show some equation, so this is sufficient. And that 39 meters per second times the 4.3 seconds gives you 167 something, but with 2 sig figs, that will be 170 meters range. Questions over part A? And what I'm trying to show you here is what's the minimum expectation. Equation, substitution, answer with sig figs and units. Now, you don't have to have the units in the substitution. I always recommend it, and I try to illustrate that in my keys, but you don't have to show the units in the substitution, but you do in your answer, obviously. Part B, if the train had been traveling over a taller bridge, would the package have landed on a different spot in the water, assume all other conditions remain the same? If so, would the package go a farther distance or a shorter distance justify? So if the bridge were higher, it would fall for a longer amount of time. We can see that mathematically from this equation. It would take longer to reach the ground. And since the displacement is both the velocity horizontally and the time that it's falling, we have to take both into account. If it fell from a higher height, it would fall for a longer amount of time. Horizontal velocity is constant, so that's irrelevant, but that same constant horizontal velocity would carry it a further distance because it has more air time falling from a greater height. So since it would cover a greater distance, it would land farther from the initial position compared to the original package. Questions on part B? All right. Number 13. A ball is thrown and follows a parabolic path shown above. Consider air resistance to be negligible. Point Q is the maximum height obtained by the ball. Points P and R are the same height above the ground. So let P, VP, VQ, and VR be the speeds of the ball at the points P, Q, and R respectively. Rank them from greatest to least, justify your ranking. Well, P and R, the speeds at that point, at those 2 points, because they are at the same height, which is given, they would have the same vertical velocity. And because the horizontal velocity is constant, if we think about their two components, the magnitude of their vertical velocities is the same, and the horizontal velocity has to be the same because it's constant. Since they have the same two components, their resultants, their hypotenuse, basically, would be equal. And so while one's going up and one's going down, speed is not a vector, so the direction doesn't matter, but their magnitude having the same vertical component and the same horizontal component would be equal. Q, however, only has the horizontal component because at the maximum height, it has 0 vertical velocity. It would still have some velocity, it would still have some speed because it has a horizontal speed as well, but it's not 0, it's only 0 vertically. So it does have some speed, but it would be less than P and Q because P and Q have that same horizontal, sorry, P and R have that same horizontal as Q does, but they also have a vertical component adding to it. So Q would be less, P and R would be equal. Questions on part A? All right. And then part B, let AP, AQ, and AR be the magnitudes of acceleration at those points. Rank the accelerations. Well, in the beginning, it said that air resistance is negligible. So the only thing causing acceleration is gravity. And since gravity would affect the ball equally at any point, we know that their accelerations would all be equal because it's just due to gravity. So the way the points are awarded here, 1 for having the ranking proper, 1 for giving a clear enough explanation of why P and R are equal for part A, and 1 explaining why VQ is minimum for part A. And then for part B, 1 point for having the correct ranking, and then 1 point for indicating that it's because they're all due to gravity. All right. I don't hear any questions, so we'll move on to the last one. So we've got our scenario here, our picture. A ball of mass 0.5 kilograms initially at rest is kicked toward a fence from a point 32 meters away as shown above. The velocity of the ball as it leaves the kicker's foot is 20 meters per second at an angle of 37 degrees above the horizontal. The top of the fence is 2.5 meters high. Assume air resistance is negligible. Assuming the ball does not hit the fence, calculate the maximum height reached by the ball. Express your answers with the correct number of sig digs in units. So it's a projectile motion question. So the first thing I always do is right away find my components. So my vertical component is going to be 12 using my sine function. My horizontal is going to be 16 using my cosine function. And my hypotenuse in both cases is 20, and my angle in both cases is 37. So I've got my two components. Now, for part A, I don't really need the horizontal one, so you don't have to do that here, but you do need to show how you get the vertical component somewhere. And then to find the maximum height, there's a few ways. Most students actually used VVAT and found the time to the peak, and then use that in the second kinematics equation to find the maximum height. I just went straight to the third equation because the third equation is basically a combination of the first two. I know that at the peak, the final velocity is going to be 0. I know initially the vertical velocity is 12. And I know the acceleration is due to gravity. So I can plug those values in and it would reach a maximum height of 7.4 meters. So that's how I solved A, but you could go a different route. If you went a different route, they would have different rounding at different points. You might get something like 7.4. And there were a few students that based on the way they rounded ended up with 7.0, but it should have 2 sig figs because our initial values of 32 meters away, 20 meters per second. I guess the only one that's really applicable here is the 20 meters per second. And then if you're counting the acceleration due to gravity as significant, then those both have 2. For part B, assuming the ball does not hit the fence, again, calculate the horizontal range reached by the ball. Express your answers with the correct number of sig digs in units. So you might have found the time for part A. If you did, you probably only found the time to the peak at part A. And so if you did that, you'd have to double it. Since I didn't approach part A that way, I had to find the time here. And so I just used VVAT, where the final vertical velocity would be -12 if the initial was +12, because it's going to go up and come back down. And since it ends and begins at the same height, its initial and final velocities would be equal but opposite. So I just plugged those in. And then I knew the acceleration is due to gravity, and I solved for time. So the entire flight time would be 2.4 seconds. Like I said, you could find it to the peak and then double it, multiple routes. And then to find the range, we know the horizontal velocity by using the cosine. So whether you did it up here or down here, somewhere you needed to show where that 16 meters per second comes from. And then the time now is found from however you found it. It could be multiple routes. And that 16 meters per second times the 2.4 seconds gives you about 39 meters. And again, depending on when and how you round, you might end up getting 38. I think if you rounded one way, you end up getting 40, but you have to show it with two sig figs to illustrate the significant figures correctly. Questions on A or B? Those are more traditionally like what we did in class. C is a little wrinkle to see if you can think through a different type of problem, but using the same kind of math. So will the ball hit the fence? Justify your answer mathematically, clearly showing all your work. So if we go back to the picture, the fence is 32 meters away. I need to know how high is it when it's at 32 meters. So my approach was, well, how long does it take to go 32 meters? Once I know that time, how high is it at that point in time? That's not the only way you could do it, but that's the way I approached it. I think it's a pretty direct method. So I horizontally know it's moving 32 meters, and horizontally I know it's got a velocity of 16 meters per second. And I know there's no acceleration horizontally. So the time to go 32 minutes at that horizontal rate is 2 seconds. So it will have reached the wall in 2 seconds. The question then is, how high will it be in 2 seconds? So now I need to switch gears from horizontal to vertical. And I use the second kinematics equation we learned, trying to find the height with a vertical initial velocity of 12, flying in the air for 2 seconds to reach that 32 meter range, and vertically being accelerated because of gravity. It would reach a vertical height after 2 seconds of 4.4 meters. Since that's greater than the 2.5 meter wall, it would not hit the wall, it would clear it. Another way you could do this is to find this time of 2 seconds and then find the 2 points on the parabola where the height is 2.5. So you could use the second kinematics equation, figure out how high is it at how much time is it when it's at 2.5 meters high. So you're actually solving for the time. And then if you do that, you actually get like 0.23 seconds. So that would be, it reaches 2.5 meters at 0.23 seconds on the way up. And then it's 2.3 or 2.2 seconds. And so after 2.2 seconds, it's on its way back down and it's going to reach that 2.5. So it reaches it on the way up and on the way down, but it only takes 2 seconds to get to the wall. It takes 2.2 seconds to reach to the 2.5 again on the other side of the parabola. So it would be past the wall by that point. So you could, I don't think that's quite as intuitive to process it that way, but a few students did, and it is a logical way to work it out. So either of those methods works. And there's a couple other ways you could go about it, but you have to in some way, prove that it is not going to be 2.5 meters or lower at that 32 meter distance. Questions on the last problem? All right. So again, as you're making your corrections, put it on a separate sheet of paper. You know the drill. Upload it on Axis. As long as you have that uploaded on Axis and it's complete by Monday night, on Tuesday I'll check, and if it's good, you'll keep your curved grade that's already in. And if you don't get it done, then I'll change the curved grade to the uncurved grade. So keep that in mind. All right. Now I just want to spend about 10 minutes going through kind of a review of some of the things we did yesterday, or 3 days ago, I guess, Monday, last time we met, and give you kind of an example problem, a reasonably simple problem, far simpler than they would typically ask you on a test, but just since we're learning it and we're kind of still got the training wheels on, still trying to get the basic grasp of this, I'll walk you through some kind of simple examples to really pull together what we started learning on Monday. So basically everything on this slide we already talked about Monday. We learned Newton's second law mathematically can be represented by sigma F equals ma. So the sum of all the forces equals the product of the mass times acceleration. And that letter we talked about, it means the sum. But we typically, while you can say it's the sum of all the forces, we usually use the phrase net force. And so you might see it written sigma F or F sub net. Either way is fine. And either way, what you really are doing is adding up all the force vectors. So it's a vector addition. And because vectors have direction, they can be positive or negative. Some of them might cancel out. You do need to separate all the horizontals and the verticals. So you factor all the horizontals together and you factor all the verticals together and you figure out, is there anything left over? And whatever's left over is what we call the net. Whatever doesn't get canceled out is what we call the net force. And so the net force is what's going to tell us how much that mass will accelerate. Now, the net force and the acceleration will always be in the same direction. So that's a key thing for figuring out what is the net force, both its magnitude and its direction. Because if we know the direction of the net force, that will be the same as the direction of the acceleration, because the net force is what causes that acceleration. So those two directions will always be the same, as long as we're looking at the net force, not just one of the components. So that's a quick review of what we learned yesterday. Now we're going to break it down into a pretty simple problem and sort of apply it. So we're thinking through, how can we find the net force for this example scenario? We've got a 5 kilogram object being acted upon by a 20 Newton force to the right. That's going to be our F1. And a 30 Newton force also to the right. That's going to be our F2. So maybe we've got a dresser being pulled across the floor by one person and pushed by another person. So both forces acting in the same direction. What is the net force on the object? So if you have some background with forces and you kind of understand what's going on here, what's the answer? If we've got someone pushing with 20 newtons and someone pulling with 30 newtons, and they're both pushing and pulling in the same direction, what's the net force? What's the sum of the forces?
50 newtons.
50 newtons, yeah. They're both going the same direction, so we just add them together. So this is one where you really don't need to go through all the steps if you understand that force is a vector and you understand they're both going the same direction, so I can literally just add them together. Just like we did with velocity and displacement. You remember the displacement story. We drove to New Jersey and back to Pennsylvania, and we just added and subtracted because they were all in the same plane. So this is a pretty simple problem that way. But I want to walk you through the steps you would do for any problem, even if it's not as simple as this. First thing you should do is draw a free body diagram, which, if you remember from last time, it is a dot that represents the object, or a box, and then arrows coming off of that dot or box to show the forces. The arrows should, in their direction, represent the direction of the force, and in their length, represent the magnitude of the force. So we start with the dot, and then we start putting the arrows on. So this example is just the exact same thing we read before. The first force, F1, it said was acting to the right with a magnitude of 20. So I draw an arrow from the dot to the right. That's my 20 Newton force. And then my second dot, or my second arrow, sorry, is going to be the second force, F2. It was 30 newtons, also to the right. So it originates still at the dot. So I've got both forces coming off the dot in the same direction. And that is my free body diagram. Most of the time, we're going to have far more than this, but that's all we know at this point. We could say, well, what about the gravitational weight? What about the normal force? Well, it doesn't actually, I said it might be a dresser being on the ground being pushed and pulled. It doesn't actually say that, though, so we don't know for sure if there's a normal force. We don't really know enough to add those vertical forces. There's no information that we could really conclude anything from. If they gave you the scenario that I did, where it was a dresser on the floor or something, then we could, but they didn't. They just says an object. So we can't really add anything else. That's all we really know for sure. And that's it. That's our free body diagram. Now, if we want to do our vector addition, just like we did before, when we do vector addition, we want to align those vectors tip to tail. So we create our free body diagram so we know that we have all the forces that are important. And then we're going to arrange them tip to tail so that we can actually do the mathematical sum, the vector sum. So we've got add the vectors. We move the second one to the start of the first one. Remember, commutative property applies, so we could have moved the first one to the start of the second one. It doesn't really matter, but we go tip to tail, and then we just add them together. The sum is just those two things added together because they're in the same plane. If they weren't in the same plane, we couldn't add them together. Or if one of them was at an angle, we would have to find the components and only add the components that are in the same plane. So just like we did with projectile motion, where we separated the horizontal and the vertical, we're going to have to do the same thing with forces. We're going to have to separate the horizontal and the vertical. And if they're horizontal, we can add them all up as vectors. If they're vertical, we can add those all up as vectors. And then we can combine them together to make a triangle to figure out the resultant. So that's the big picture of where we'll be going eventually. But these are both horizontal, and they're both actually even going the same direction. So it's a pretty simple scenario to consider. So in the end, we can recognize that the sum of those two forces is just the vector that represents the length of them. Since there's no angle, we can't really create a triangle, but it would be the length of them. And therefore, mathematically, we said that they were both acting to the right. We could either use the word right, or we could define the to the right as positive and just say it's positive 50. Down here, we're just showing if we add them together, we get 50 to the right, or you could say positive 50 newtons if you've defined right to be positive. But the forces are to the right, so the acceleration would also be to the right. Questions about that? Like I said, a fairly straightforward example, but I want you to think through all the steps that you would need to take if it wasn't quite so simple. So you would never actually see a question quite this easy on an AP exam. They might ask you a multiple choice question like this, but they wouldn't actually ask you probably to find the net force. What they would probably do is ask you what comes next. Same scenario, but they would probably say, what's the acceleration? And they would expect to find the acceleration, you have to determine the net force. So I don't think I've ever seen a question quite so simple where you can literally just add 20 and 30 and say the answer is 50. But they might have one that says 20 and 30, and then you've got to figure out that the net's 50, and then from that, find the acceleration. That would be a legitimate level for, multiple choice question I could see. So how do we do that? Any ideas? How are we going to find the acceleration now that we know the net force is 50?
Divide by the mass of the object, because the force is in kilogram meter per second squared. So if we divide out the kilograms with the mass of the object, we'll get the meters per second squared.
Good. So if we think through the dimensions, if we think through the units, we can logically process that. What law can we use to solve this?
Newtons, the F equals ma. I don't remember what number it was. Second. It's on the
Yeah.
slide.
Yep, it's the second one. Yep. So up here we got a little hint, Newton's second law. So if we use Newton's second law, we can actually do without having to prove dimensionally. It does work dimensionally, but we can prove that Newton's second law tells us that net force is going to be the mass times the acceleration. So the acceleration would be the net force divided by the mass, like Ethan said. And since Newtons are kilogram meters per second squared, if we divide out the kilograms, we're left with meters per second squared. And as we mentioned before, if the net force is to the right, then the acceleration will also be to the right. The net force and the acceleration always go the same direction, since it's the net force that causes the acceleration. Okay, any questions about this example? All right, one more quick example, just one slide, and then we'll be done with that for today, and we'll give you some time to work. So another question might be, what is the net force acting on a 2 kilogram object below? And they give us this free body diagram that shows there's an upward force that is equal and opposite to this downward force. There is a rightward force, and there is a acceleration of 1 meter per second squared. So we know force is a vector, and we need to figure out what's the net for this scenario. If we look at the forces vertically, because again, like we did with projectiles, we want to separate the vertical and the horizontal. If we look at the forces vertically, they appear to be equal and opposite. So if we add them together, they cancel out. If this one, we don't know what the value is, but if this was positive 10, this would be negative 10, positive 10 and negative 10 give us a sum of 0, a vector sum of 0. So there is no net vertical force. Horizontally though, so once we've kind of canceled those out mentally, horizontally, there is only one force horizontally. And so that force is the net force horizontally, and actually the net force for the whole object because the vertical one's canceled out. So that net force, that F3, is what's causing that 1 meter per second squared. We can figure out the value for that because it says the object has a mass of 2 kilograms. So since we know the net force is mass times acceleration, this acceleration is 1 meter per second squared, the mass is 2 kilograms. And so thinking through this free body diagram and recognizing that this force is the net force, we can determine it would have a net force of 2 newtons to the right. So a couple fairly simple equations, or a couple simple examples, sorry, to use Newton's second law as an equation and the concepts of free body diagrams to sort of process some basic questions. Just want to keep your brain thinking about forces. We spent most of the period reviewing back on kinematics. So I wanted to do a little bit of thinking about forces. Monday, we're going to kind of wrap up a lot more about forces and several different applications. But just so you recognize, we've pretty much covered all the new information about forces. It's just basically Newton's laws. But then while there's not that much in terms of content, there's an almost unlimited number of applications to it. And how do we apply trig, and what kind of force is friction? So we'll be learning about some specific kinds of forces as we go and adding that in, but it still all comes back to Newton's 3 laws. So this is the foundation. So we'll keep hammering home this foundation over and over again. But on Monday, we'll start digging into friction and tension and some things that are at slopes to find how the trig factors in. And then when we come back from Thanksgiving, we'll go into even greater and more complicated scenarios. But all comes back to Newton's 3 laws. So if you really understand what we've done here initially, that's the foundation of everything we're going to be building on the rest of this couple of units on forces. All right, so we have not quite 20 minutes left. With this 20 minutes, you can do what you need to do, whether it's finishing your corrections and uploading those to Axis, whether you want to focus on getting positive physics worked on, or if you have something else that's more pressing, your choice. If you have questions for me, I'll keep the Zoom running till 11:25 and be glad to hang out and answer any questions you might have. But if you don't have any questions, you can be dismissed. And I hope you have a great weekend if I don't see you tomorrow.
Thank you.
Thank you.
You're welcome.
Thank you.
Hey, Mr. Webb.
You're welcome.
For my corrections, I got one wrong just because I had well, not wrong, but I got points off because I had north of east rather than east of north.
Mm-hmm.
And
did you have the wrong angle with it? Because you can give it in either direction, but did you have the wrong angle with those directions?
Yeah, I had the angle for east of north, but wrote north of east.
Okay, gotcha. Yeah.
So for my corrections, can I just write it down correctly?
Yeah, just say I just had the correction. Just say, I had the direction wrong. It should be this. That's it. You don't have to redo the problem.
Okay. And for number 12A, I think I missed it, but is the answer around 7.3 meters?
Yes.
Okay. All right then. Thank you.
All right. You're welcome.
I just had a question. Is there a way for me to see the videos of class for the previous ones?
Yeah, they're always on YouTube. So if you go to the links section on the bulletin board page of Axis, where it has the link to the Zoom and the link to positive. Yeah, there's a link there for my YouTube channel as well. And so I actually have all of them recorded.
Cool.